I want to do an example of physics problem solving in one of the most straightforward examples, one of the most straightforward circumstances, the example of uniform motion, constant velocity motion. And I will have a specific example we're going to work on here, but this example is intended just to illustrate the physics problem solving strategy that I use in practically every motion problem or every physics problem that I'll ever do. And so I'm going to illustrate that here. First step is we read the problem. A soccer player is 15 minutes from the opponent, or 15 meters from the opponent's goal, and she kicks the ball, and when she kicks it, after it leaves her foot, it moves at constant velocity across the field. We're making approximations here. After half a second, 0.50 seconds, it passes by a defender who is 5 meters away from the kicker. And the question is, how long does the goalie have, goalie standing at the goal, how long does the goalie have to block the ball before it enters the goal? That's our question. So how do we attack this? How do we make sense of this question? Well, there may be ways you can do shortcuts or just sort of look at it, squint, and do things. I want to show you the standard systematic problem-solving strategy that will work in every physics problem ever. Step one. Always step one is the prepare step. Do things you need to get ready to solve the problem and to think about it, to frame it mathematically. So the prepare step always includes drawing a picture. Almost literally always. Pictures are so helpful in setting up physics problems. You'll understand what's going on so much better. You can label things. It's great. You're going to draw a picture. What else? You'll list known and unknown data. Knowns and unknowns. Maybe you'll choose coordinates a lot of times in this step. There's a lot of prepare stuff that you can do. Some people will draw a graph in this step. Some people draw a motion diagram depending on the problem. This is the step one, the prepare step. So let's see how that plays out for this problem. I will draw a picture. I've got my soccer player. She's just kicking. She's kicking. Kick. Here's the ball moving forward. I probably should have left some space here. Ball moving forward. Okay. Here is a defender a little ways down the field. And here's the goalie farther down the field. Let's see, I need a goal back here. Goal one, soccer goal coming up. My artistic skills are not my strong point. Okay, so one soccer goal coming up. Okay, cool. Okay, so we have here our, there probably needs to be something here. Okay. All right, we have here in this picture a picture of what's going on. We've got the ball being kicked. It's going toward this person, past the defender, and all the way to the goal at the other end. And what can we do? I've got my picture. When I have a picture, I want to label it. I want to put in some labels. So in particular, I will label this position to be the kicker's position. I'll call this, when the ball leaves that position, I'm going to call it T kick and X kick to represent that position, that information. And here, this will be time when it passes the defender, TD, and XD, X when it passes the defender. And I'll label this time when it reaches the goal and position X when it reaches the goal. So I've labeled those points along the way, those 3 points for time and position. If the ball's velocity were changing along here, I'd probably also be labeling velocity at the kicker, velocity at the defender, velocity at the goal. But it turns out those are all the velocity is constant, so I'm not going to bother writing that down. So okay, I should also maybe choose coordinates here. So I'm going to choose, for convenience, x equals 0 at my initial point where the ball is. That's often a good choice. It doesn't have to be. You can choose coordinates any way you want. Every coordinate choice is valid. Some are just more convenient than others. X equals 0 here, and I'm going to choose the plus x direction to be to the goal. Some other person might have chosen x equals 0 at the goal and plus x to be distance from the goalie, right? Anything's fine. The defender could have their own coordinate system. Plus is that way, and it starts negative. Whatever, but we've chosen our coordinates now. And I can look at this. That's my coordinate system. That's my setup, and I can make a list of known data out of all of this. Oh, I'm also going to choose, if this is my x equals 0, I'm going to choose the moment of the kick as time equals 0 as well. That's also an arbitrary choice, but I get to make it. So I'm going to choose this time to be time equals 0. All right, I have all that set up now. So what do I know? Well, let me make a list of knowns and unknowns just to keep track of this. I know that time of the kick is 0 seconds. That x of the kick is 0 meters because I made those choices in my picture. I know that the time the ball passes the defender is 0.50 seconds. I know that the position of the defender is 5.0 meters. Excuse me. And over here, time to reach the goal, that is my great big unknown. That is my goal overall in this, is to figure out time to reach the goal. X goal, the position of the goal, is 15 meters. And again, I can write that down now that I have a coordinate system. I can write that down. The other thing that I don't know, that's not known anywhere here, I'll put it somewhere down here. The velocity is also an unknown for me. That's another thing that's not given in the problem. I don't know the velocity. I guess I should call it Vx. Well, I don't know the velocity of this ball. I'm using v sub x to be velocity because it's velocity in the x direction. In general, as we move on in physics, we'll find x and y and z and all these things. So we have to keep track of directions. I'm keeping track of it now. Okay, so that's my prepare step. I've prepared by listing a bunch of stuff I know. This is great. I've made it a bit cluttered, but that's okay. Small board. Right, so next step. Always the next step is the setup step. This is where I figure out what physical principles are involved, what concepts in physics are involved, and I figure out how I'm going to represent those concepts mathematically, how I translate them into math. And so, in particular, this means the setup step might be using the story of the picture. This is choosing equations or anything else, any other mathematical modeling stuff you need to set it up. So choosing equations. For this, I'm at constant velocity. What does that tell us? Well, because we've got constant velocity, Vx equals delta x over delta t. Basically, if you're at constant velocity, then the velocity equals the average velocity at all times. So we can just write down velocity equals average velocity, delta x over delta t. Or, in other words, this tells me that delta x equals Vx times delta t. Or another way of writing this, if I want to write it out explicitly, I can say x final minus x initial equal, oh, this is too cramped, isn't it? Never mind, I'll go to another line. Fine, fine, fine. So I can say x final minus x initial equals Vx times t final minus t initial. Sometimes people will leave out the x initial and the t initial or something. They'll leave out the t initial because they always assume t initial is 0. I'm going to put it in because that is delta t, and we can make a lot of choices for this. I could even write this as x final equals x initial plus Vx times t final minus t initial if I want to solve for x final on that side. Doesn't really matter how we write it. But okay, that is the only relevant equation for constant velocity motion. Every constant velocity problem can be solved in terms of just this definition of velocity in terms of final and initial points. The thing we're going to notice here, though, is that initial and final are actually kind of general concepts. I can maneuver around what they mean. So one natural choice for initial and final would be the initial moment to be the kicker, the kick of the ball, and the final moment to be passing the defender. I could use those. That's an initial and a final. So for us, in our setup, in our problem setup, I can say, okay, fine. I can say that x of the defender equals x of the kicker plus my constant Vx times t of the defender minus t of the kicker. I can say that. That's a perfectly good equation. I could have said it another way. What if my initial point is the kick and my final point is the goal. I could say x goal is final equals x kicker plus Vx times my final time is t goal minus t kicker. I could say that. That's perfectly reasonable. Or, keeping going, I could also say, heck, maybe my initial point is when it gets past the defender, my final is when it hits the goal. I'm just saying you have choices here, right? I could say x defender, or sorry, final is goal, I said. I could say x goal equals x defender plus Vx times t goal minus t defender. That's also a valid equation. And as long as I have a delta x and a delta t, initial and final, I can do this. This is great. Okay, so I've set this up, and to finish my setting up, to do this effectively, to make this useful, what I want to do is I want to take advantage of my choice of coordinates. I chose x equals 0 here for a reason, because it was going to be handy. I chose t equals 0 here for a reason. It was going to be handy. I get to, at this stage, I'm going to hold off on plugging in most numbers. I don't want to plug in numbers right away, but I am going to plug in zeros right away because that'll tell me which equations are going to be easy to use. So in particular, x kicker and t kicker, I can call 0 wherever I see them. So this is going to be 0, this is going to be 0, this is going to be 0, and this is going to be 0. You can see, if you imagine erasing those things, plugging in those zeros, that these two equations have simplified a lot. This one hasn't simplified at all. And the other thing we have to do in setting up our equations is say, what are my knowns and what are my unknowns? And if you plug in numbers, you'll be able to recognize the unknowns because they're the only things that are still variables. I hate plugging in numbers too early. Instead, a trick you can use, I've been doing this for years. I sort of keep track, I don't know t goal, I don't know Vx, I can just keep tracking it in my head. But early on, one trick that I've seen some students really appreciate is underlining their unknowns. T goal is an unknown. Vx is an unknown. So I'm just going to underline those so that those symbols stand out to my eye. T goal and Vx are my unknowns. T goal is here, T goal is here, Vx is in all three of these. All right, so now I've set up my equations, and if you've done some math, you probably have heard the phrase, you've probably heard people say that if you have two unknowns, then in general, apart from some pathological edge cases, you need two equations to solve for two unknowns. If you have 5 unknowns, you need 5 equations. If you have 1 unknown, you just need 1 equation. N equations in n unknowns. Because I have 2 unknowns to solve for, in general, unless something weird is going on, I'll typically need 2 equations to do that. And so I need to choose 2 equations. I want to make sure that at least one of them has the t goal in it, because that's my ultimate goal. And I want to choose another one to, if I need to, simplify it out. So these 2 equations both have t goal in them, but this one I was able to plug in a bunch of zeros to make it easier. This one is still ugly. There's still lots of terms that I need to keep track of. So I like this equation. That looks like a good one. And then this equation, though, has 2 unknowns for it. I can't just solve for t goal because there's also the velocity that I don't know that's an unknown. So I need a second equation to solve for velocity. It could be this one, 2 equations and 2 unknowns. I could solve that. But this one is going to be way easier. So this will be my second one. I'm going to find 2 equations in 2 unknowns. Again, more general problems, you might have 3 equations and 3 unknowns. Probably you're not going to have 6 equations and 6 unknowns unless you're doing something really complicated. But 2 equations and 2 unknowns, 3 is pretty typical. So okay, I've got this. Let me write them down in simplified form. The first one says x of the defender equals Vx times t of the defender. And I'm going to keep underlining Vx to remind myself that's an unknown. And x of the goal equals Vx times t of the goal. And here, I can underline both of those because they're both unknowns. So okay, there I now have 2 equations and 2 unknowns. And I want to emphasize, after step 2, the setup step, the physics is done. In my classes, if on an exam you were to get to this point, say 2 equations and 2 unknowns, and say I can now solve these two equations and two unknowns using algebra to find t goal. That's my answer. If you wrote that down and did all this correctly up to this point, that would be, I think that would come out to give you a 9 out of 10 score on my exam problems. That's how much this is the physics being done. There's still algebra left to do it. And that is, in fact, step 3. Step 3 is the solve step. Solve the equations. Step 3 is always solve the equations, and I guess I don't really need to do this. I like underlining the unknowns and doing that. Some people like putting a little list of unknowns on the side of their paper and checking them off as they figure them out, or writing down the answers as they figure them out. For us, we're just going to solve. So let's do this. When I look at this, let's see, I need to find these things. This equation, I can find Vx right away because there's only one unknown in it. I can find that my velocity is x of the defender divided by time of the defender. I can plug that in even. X defender is 5.0 meters. And time of the defender is 0.5 seconds. And putting it together, 5 divided by 0.5, that looks like 10 meters per second. So now, my Vx is no longer an unknown. Now it is 10 meters per second. I have a value for that now. I found it. And then I can come over here and take my other equation, plug that in, say t goal is equal to x goal divided by Vx. And I know those things. X goal was 15 meters, and Vx is 10 meters per second. I've written those down, 15 meters, 10 meters per second. I notice that the meters cancels out, top and bottom, my units cancel out, and this 1 over seconds comes out to seconds. This is great. I'm going to get, squeezed in the corner, 1.5 seconds as my final answer for this problem. The goalie has 1.5 seconds to stop the ball after it's kicked, based on this information. That's step 3. You think we're done? Basically we're done, but there is one more step I want to emphasize. The board's full, so I'm going to have to erase something. I like my picture. I'll erase my setup just for the moment. Step 4 is assess. We're going to check stuff. Check to make sure it makes sense. You're going to think about it. Is this a reasonable answer? In this case, so things that I'll tend to check here. I'm going to say, are the units right? Units right? Order of magnitude. Is the order of magnitude right? Anything else, is it sensible for the problem? Anything else is reasonable. So, for example, if I had gotten a time of 10,356 seconds, that would be weird for a soccer game, right? That would be way too much. If I had gotten a time of like 3.6 microseconds, that would also be a pretty impressively fast kick for a soccer game. I expect having a second and a half to react, that sounds like something that is reasonable for soccer. So that makes sense to me. The units canceled out to be seconds, and so that time should be that is a unit of time. That's reasonable. Right order of magnitude, and in general, we could have done this intuitively, right? I can see that the defender is 5 meters, the goal is 15 meters. That's 3 times farther away. At constant velocity, that's 3 times as long, 1.5 seconds. Obviously, I could have done this a lot faster. But so if I can do a check like that, it really solidifies my reasoning on the rest of this. But that's my story. That's how I've solved this problem. I drew the picture. I labeled data about each one of the interesting points, interesting events in the problem. Each event gets labeled time, position. If we're changing, I'd label velocity for each one too. I made note of the fact that it was constant velocity throughout. If it had been constant acceleration here and constant velocity there, I'd have to use different equations for each one. But then I said, okay, I'm going to set up the equations that are relevant. Because it was constant velocity, it was just one equation, but I had to use that one equation in 2 different circumstances, applied to 2 different systems, 2 different initial and final pairs, to be able to do it, to be able to solve it. And then I did the math and assessed whether it was right. And that's what I came up with. So I hope that gives you a sense then of how you can solve a uniform motion problem in particular, but I hope it also gives you a sense of a strategy you can use to solve physics problems no matter where they come up. You use the same strategy no matter how complicated the problems get.